I'm Hiroka. I'm from Windsor Polytechnic Institute, and I have been working with Adrian, and he's been a great mentor to me. Today, I will be talking about dynamical influence of the time-evolving Milky Way on the population of stellar streams. So what are stellar streams? The Milky Way galaxy is a fairly large galaxy, and there are smaller galaxies around the Milky Way. And these smaller globular clusters or dwarf galaxies get pulled by the Milky Way's stronger gravity and fall into the Milky Way. While they are orbiting around the Milky Way, they get stretched out by the tidal forces from the Milky Way and form what we call stellar streams. The Milky Way halo used to be believed it was completely smooth and not interesting, but it was discovered that, actually it was discovered by my thesis advisor, Professor Heidi Newberg, that the Milky Way halo was actually full of stellar streams. And now nearly 100 stellar streams have been discovered in the Milky Way. And this is the Sagittarius stream, which is the largest stellar stream in the Milky Way. And this was created by a body simulation in my home institution. And we created a dwarf galaxy we model this dwarf galaxy by a bunch of particles to represent stars in the dwarf galaxy. And as you can see, starting from a spherical shape, the dwarf galaxy gets stretched out over time. So in this project, we run very similar stream simulations, but we used a different simulation technique, which runs so much faster than a body simulation. So there are a lot of exciting measurements that we could potentially make using stellar streams related to dark matter. For example, the dark matter subhalos are predicted to interact with stellar streams and cause gaps and density variations along streams. But we also know that interactions with baryon in the Milky Way can also have similar impact on stellar streams. And this study of a Palma 5 globular cluster showed that a stream on prograde orbits with respect to the galactic bar can have a gap along the stream. So this implies that streams on retrograde orbits or streams with large pericenter, large orbits, can be potentially used to detect dark matter subhalos. So that motivates what we are trying to do in this project. We are interested in the morphology and the statistical properties of streams impacted by other baryonic structures in cosmological simulation, so we can distinguish these baryonic interactions from dark matter interactions. Okay, so in our simulation, we model the Milky Way using the fire simulations. The fire simulations are cosmological zoom-in baryonic simulations which produce the Milky Way-like galaxies that are consistent with the observation. Okay. So this is the fire simulations that we used to model our Milky Way galaxy. And M12I is a Milky Way-like galaxy, but this has a smaller bar. And this is a relatively quiet simulation, meaning that there is no massive merger events going on in the past several giga years. But this video started from the beginning of the formation, but we used only past 5 giga years from the present day. And we model this M12I galaxy by using existing time-dependent basis function expansion of M12I by our et al. And basis function expansion is an approximation technique to replace complex functions to Poisson's equations. And they extracted the potentials from the Fourier simulations by fitting the potential at each snapshot by using spherical harmonic expansion for the dark matter and azimuthal harmonic expansion for baryons. And if you remember from quantum mechanics, as the degree L goes larger, then harmonic expansion gets more complicated. So the resolution of the simulation gets better. And in our case, the maximum L is 8, which is still low order expansion. So this simulation does not include low mass subhalos due to the resolution. And also, in order to investigate which component of the Milky Way is affecting stream morphology, we axisymmetrize both components by keeping harmonics only when L is even for dark matter, and M is 0 for baryons. Okay, so we run 1,000 global cluster simulations with M12I galaxy using particle space algorithm. And we fixed progenitor parameters, but we varied orbit parameters for all 1,000 simulation runs. And this is one snapshot of our simulation. And this human organ-looking object is the M12I galaxy, and this is our simulated stream. And here is the progenitor of the stream, and that arm goes closer to the galactic center is leading arm of the stream. The arm that goes behind it is called the trailing arm. And we start our simulations from the current position in the sky, and then we integrate this body as a point particle 5 gigayears back in time, and then starting from this position in the past, we integrate this body 5 gigayears forward in time to match to the current position, while releasing particles to form a stream. Okay, so this is a movie of one of our simulations. In our actual movie, it's a 3D movie, so you can rotate around while you are playing it. But this is how our simulation looks like. Okay, since we are interested in stream morphology, we are trying to analyze our simulations in phi1 and phi2 stream coordinate systems. And the phi1 and phi2 coordinates are just stream longitude and latitude coordinates, and then we place progenitor at the origin, and then we rotate both arms so that the leading arm of the stream is the positive phi1, and then the trailing arm of the stream is the negative phi1. And this is just one of 1,000 simulations. And we run both of the simulations with axisymmetrized dark matter and baryon. And this simulation was run with present-day static Milky Way potential. And this simulation was run with time-dependent Milky Way potential. So time-dependent Milky Way potential definitely has some effect on this stream morphology. Okay, so in this case, we asymmetrized only baryon, but we kept the full complex dark matter. But both of the simulations are looking a little bit skinnier than fully asymmetrized cases, but full complex dark matter doesn't seem like doing much to both streams. And in this case, we used the full complex Milky Way potential for both of them, while static cases are not doing much to this stream. Using full complex time-dependent Milky Way potential destroyed this stream. And again, this is just one example of 1,000 simulations that we run. So we are trying to summarize all of our simulation runs by using statistics. And here, we computed variance and skewness of all 1,000 simulations in phi1, the stream length. And they are colored by pericenter because most tidal disruption happens at pericenter. And these two are both dark matter baryon asymmetrized, and these two are only baryon asymmetrized. And these two are full complex Milky Way potential. And these are all static cases, and these are live cases. And all static cases are pretty similar to each other, but these live cases show that the streams with live potential are more complicated than static cases, especially the full complex live Milky Way potential. And this figure shows that the streams with smaller pericenters are more complicated structures than streams with larger pericenter. And this is just one example of full corner plot of all statistics that we are trying to compute. And this is the same panel as the previous slide. And here we are trying to compare stream properties of each Milky Way potential case to the full static Milky Way potential case. And we computed the difference between leading arm and a trailing arm of all 1,000 streams. And then we took beams in pericenter, and then we compare each Milky Way potential case to the full static potential case. And using live potential case causes more asymmetry between leading and trailing arm. And the full live case is the most different from the full static case at smaller pericenter. And in this figure, we computed the width of all 1,000 streams. And again, full live case is the most different from the full static case at smaller pericenter. Okay, so we still need to find what baryonic features are actually affecting the morphological differences in all of our simulations. And we don't think it is the bar, and we don't think it is the satellite dwarf galaxies in M12I, because we actually tracked the orbits of the most massive satellite dwarf galaxy in M12I, but it didn't seem like he was doing anything to those streams in our simulations. And we believe it is mostly the structure in the disk, but we still need to look into what it is actually doing to those streams. And we also want to understand if the time-dependent dark matter structures also play any role in this, and if there are any conditions that dark matter dominates this stream morphology. And since we developed this technique to separate complicated Milky Way structures, we could potentially use streams to better understand the dark matter substructure. Thank you.
All right, questions? Oh, Amiel?
I understood. The reason why there's a difference between static and more complicated, is that because the dynamical timescales for the full galaxy and the streams are about the same? Is that the reason?
The static case doesn't really depend on time, so it's just only one snapshot at present day. But the live case is like this. Maybe this one. Oh, I can't play. Oh, but yeah. So this M12I galaxy started from nothing, and then it's growing over time. So the mass is also increases. So I think that's one of the reasons that these two simulations are different. And also these baryons are rotating.
Yeah, no, I understand.
Over time.
Yeah, I understand that difference, but I'm saying it's because the galaxy itself is growing on a timescale which is roughly the time at which the stream itself is moving around. Mm-hmm. That's because they're comparable. That's the thing. Yeah. Okay.
Other questions? Tumin?
Cool. When you showed the Milky Way, you had showed multiple streams together. And I was wondering if in your simulations you ever had a case where there were multiple streams, or if it was always one stream at a time.
We are doing one stream at a time. And actually, in my home institution, someone else is working on multi-dwarf galaxy simulations, but it's kind of difficult to come back to the actual position using multi-dwarf galaxy at the same time, because these dwarf galaxies are also interacting with each other. So it's kind of difficult to do multi-dwarf galaxies at the same time in one simulation.
I see another question. Yes?
Yeah, thank you. It's very good. And I think, so a lot of the stuff which had very small pericenters was the things that were affected most. So I don't know if you know like kind of what hope there is to actually have an observable of something in like the inner part of the halo that could like maybe tell you about how strong the baryon feedback is in like real life, like if you took actual streams. And could you like kind of maybe try and set constraints on something like,
If you take actual stream in this simulation, you mean?
No, so motivated by this, do you think you could motivate something, like some observable in like the inner part of the galaxy that could inform you?
I don't think I understood
the
your
baryons.
question.
Okay. Well, maybe I can ask you after then. But yeah, but thank you anyway.
Thank you, Hiroka, again.